All right, we are moving into the next section of work and energy. This is section 6.5. Um, in this section, we are going to take a look at a physical application of the integral, and that is calculating work, the amount of energy it takes to do something. So from physics, we have a formula here. This would be a scalar formula, a scalar version of the formula from physics. In this case, work is force times distance. So if there is a force and you are applying it to move an object, so for instance, let's say, maybe we're pushing something along the ground, there's going to be this kinetic force of friction that we have to work against. So it's that force we have to overcome. So it does have to do with overcoming or fighting against a force of some kind. Okay, if you have taken many physics classes, you will have seen this formula in lots and lots of different contexts. For instance, you might see something like this, which is a little bit more what I'm familiar with, and you will see plenty of that in Calc 3. But for now, we're just going to think of it as force times distance. So, in example 1, how much work is required to lift a 50 kilogram box? The dimensions of the box are 1 by 1 by 1 to a height of 1 meter. So, you don't need to draw a picture for this, but sometimes it is useful. So if you have this box sitting on the ground and you want to lift it up a certain amount, so we can think of this top plane here. So this weighs 50 kilograms. So we have to move this up 1 meter. So then we get just another copy of this box, but above it, a distance of 1 meter. So something exactly like that. Okay, so this distance that it moved is 1 meter. So for force times distance, we are fighting against the force of gravity. So this lifting process is against gravity. And when you go against gravity, you have to figure out the force of gravity acting on an object. So the force of gravity acting on an object is, in this case, so for gravity, I'll do F sub g for the force due to gravity. This is the mass of the object times g. So here, m is the mass measured in kilograms. And then g, right here, is the acceleration due to gravity. This is a constant. It is measured. So this is 9.8 meters per second squared. This is a constant that will show up in the class. In many application problems, we'll be using this g. I keep this in my problems written as g. I don't replace in 9.8 in my final answers because this is a physical constant of reality. Everybody knows what g is that does these kinds of problems. So it's fine and acceptable for you to write your answer in terms of g. All right, so once we have that information, what the force is we are working against, and what this acceleration due to gravity constant is, we are ready to calculate this. So I'll call this part 1 of the problem because there is another question that they ask. So here, work is the force against which we are acting times the distance through which we move against that force. Force? Something like that. So here the force would be the mass of this box, so 50 kilograms, times the acceleration due to gravity, times the distance, which is 1. So the work is 50 g, and the units are joules. And then I'll round this up or whatever. I'll get a decimal. This is 490 joules. Okay. So for number 2, we want to know stacking 4 boxes on top of one another. Okay. So the first box that's on the ground, we're not moving it. It's just on the ground. So there is exactly 0 work because we're not moving it at all. The second box that we move is exactly what we just figured out earlier. It's what happens if we move it 1 meter. So this would be our 490 joules. But the third box would have to be put on top of the second box. And the second box, right, if you think about stacking these boxes on top of one another, this is the box number 1, number 2, number 3. So this distance, we'd have to move a box up to number 3. We would have to lift it 2 meters. So this would be our force from earlier, so 50g times our distance is now increased to 2 meters. So this would be, yeah, I won't get a decimal for that because I don't have a decimal for that written. Even though it's very easy to calculate since g is a nice number. So then work number 4, we do the same thing, but we have to move this box up just a little bit higher. This box on the ground would have to move this entire distance, which is 3 meters, to get up here. So this would be 50g times 3, and each of these are joules. So the total work here, total work, if we add these all together, W1 plus W2 plus W3 plus W4, this is 2,940 joules. All right. So for the remainder of these problems, we're going to be working with a force that generally changes. It's going to be changing for various reasons. There's a couple different examples that we can take a look at here. So essentially what we're going to do, if your force is not constant, if your force is continuously changing, then that means we're going to need an integral. Okay, so an example of this where the force is not constant is, consider a spring. Okay, if we are going to compress this spring, let's say we compress it from, or actually let's say we stretch it, because that's going to take force too. I just want to work with some nicer numbers. So let's say we stretch this spring by some amount. Hooke's law tells us that the force of a spring that obeys Hooke's law is negative kx. The negative sign means the force is in the opposite direction in which you compress it. So for instance, if we compress our spring, then the x value is negative because we're compressing it, we're making it smaller. And a double negative would give us a positive. That means the spring's going to push back when you compress it. However, if you stretch it, so our x value, the amount we stretch it, would be positive, in which case the force would be negative, trying to pull back. This is called a restoring force because it tries to restore itself to its equilibrium. So what I mean by that is we can take this right here to be the spring's natural length. It's what it is. It doesn't, if you try to compress it a little bit, then the force pushes back this way. If you try to stretch the spring, then the force wants to go back to this natural length. The spring is always trying to return to this length, its natural length. So if you wanted to know the total amount of work it would take to stretch the spring, let's say, so let's say total work to stretch the spring 5, let's say, whatever, 5 somethings, let's say meters. This is a huge spring. To stretch the spring 5 meters beyond its natural length. Then we'd have to use the idea that we're going to integrate the force. And then this dx here, this actually is like our little distance. So we figure out the force acting when we move a small amount beyond that little, that current x value. So this formula changes a little bit. It's going to be the work is the integral force. So in this case, we would have negative kx dx from 0 to 5. So in this way, if your force varies continuously, then it's going to be the integral of force to determine the work, I should say. Okay, so there is this, we are going to go through this procedure on all of these problems for the most part, and so this is going to become ingrained, but essentially what we want to do is, like many problems in Calc 2, we split up the problem into lots of little pieces or chunks. We figure out the amount of work it takes to lift each little chunk, or whatever operation we're doing. Then we have built the integral, and we will finish it off with an integral. So we will take a look at this in example 2.